Project scheduling. In this unit, we will review the techniques used for project scheduling. We will review three popular planning methods. We will go through examples of Gantt charts along with CPM and PERT tools. We will use an activity on node network, which will be analyzed using both forward and backward passes. We will analyze the project activity network for its critical path and any available slack time. Different techniques are used for scheduling project activities. These techniques ensure precedence, timing, and effective management of the project. Project scheduling includes settling realistic time and cost estimates. This is both an art and a science. Estimates must include a thorough analysis along with managerial judgment. The goal is to ensure the optimal use of resources, including people, money, and materials. The three most common project management techniques are listed here. Next, we will discuss each in detail. Here's a simple Gantt chart. Tasks are listed on the left, while horizontal bars indicate the duration of each. Note that there is no relationship shown between tasks. In other words, we don't know if one task must be completed before another. Here's an example of a Gantt chart showing the tasks associated with servicing a jet aircraft. This chart is more complex, yet describes a set of activities measured in minutes, not days or months. PERT and CPM use network techniques to manage projects. Both techniques were developed to manage very complex and expensive projects. They include task relationships and interdependencies. The two differ by the method used to estimate task duration. Both PERT and CPM use 6 steps to create the project plan network. Activities are defined with descriptions, resources, and timing. They are then linked by their relationships. Next, the critical path is identified. The critical path defines the project's constraints and indicates the longest time path through the network. If the critical path is late, the project will be late. Finally, the network is used to manage the project team. The PERT and CPM tools will help the project manager answer these questions and others. Activities are separated into critical and non-critical to help the project management focus their efforts. The project cost, schedule, and resources can be managed this way. Activity on node is one method for charting activities. Each circle in the chart represents a single activity or task. The arrows reflect the relationships and precedence between activities. The first series indicates that activity A comes first, followed by activity B, and then C. In the second series, activities A and B must both be completed prior to the start of activity C. Finally, the last diagram shows that activity A must be started before B and C. Here's an example of activity on node charting in action. We start with a list of activities and their predecessors. For example, activity C cannot start until activity A is completed. These activities are necessary for paper manufacturing. Here we start charting the activities. We add a start activity to begin the project. Activities without predecessors are tied to the start activity. From these initial activities, we build out the chart as we add new activities based upon their predecessors from the table. This figure shows the completed AON network for these activities, linked by their relationships. We see the flow of all activities from start to finish at point H. As previously mentioned, identifying the critical path is key to effective project management. The critical path is the longest path through the network and defines the overall length of the project. Any delay of the critical path delays completion of the project. Slack time is the amount of time an activity may be delayed without affecting the overall project. Activities on the critical path have no slack time. Once the chart structure has been defined, we add the time duration for each activity. Here is a list of the activities identified earlier. The time required for duration of each activity has been added. Note that the actual project length will not be 25 weeks, since some activities will occur in parallel. In the next discussion, we will build upon this structure to take advantage of these tools. To perform a critical path analysis, we need to understand the 4 times associated with each activity. The earliest start represents the earliest date that an activity can be started. This is typically driven by the completion of preceding tasks. The earliest finish is simply the earliest start plus the duration of the current activity. The latest start is the latest an activity can start without affecting the outcome of the overall project. Again, the latest finish is the latest start plus the duration. Here's the schematic displaying the structure of the activity format. You should memorize the location of each item to fully understand the data presented when viewing a project plan using these symbols. Start is on the left, finish is on the right, earliest is on the top, latest is on the bottom. The activity identifier and duration are listed in the center. When the scheduling tool completes an analysis of the activity dates and durations, it begins with the forward pass. The forward pass starts at the beginning and works its way to the end or finish. At each activity, the earliest start equals the maximum earliest finish of all immediate predecessors. The earliest finish equals the earliest start plus the activity duration. This is the process used to determine the overall completion date of the project. We start by creating the starting activity. For the Milwaukee paper example, as for most projects, the starting activity starts at earliest start equal to 0 and the earliest finish equal to 0, since the activity has no duration. Next, we add activity A, which has duration of 2 and thus an earliest finish of 2. These numbers are calculated using the rules stated previously. We link the start activity to activity A, and then we add activity B with duration of 3 and an earliest finish of 3. After linking the start, A and B activities, we add activity C. The activities are linked based upon their precedence. Notice that the earliest start and earliest finish values are added as we go. Since activities A and B precede activity D, the earliest start of D is the larger of the earliest finishes for activities A and B. Again, the earliest finish is the earliest start plus the duration. Now activity D is linked to its predecessors. Using the same logic, we complete the activity network with the remaining activities. This completes the forward pass analysis. Note that the earliest finish of activity H, and thus the length of the overall project, is 15 weeks. Now we complete the backward pass analysis. We begin with the last activity and work our way backward to the start. The latest finish time rule states that the latest finish is the minimum of the latest start of all following activities. For the backward pass, the latest start time rule is that the latest start equals the latest finish reduced by the activity duration. We follow the backward pass rules by starting at the end with activity H. We set the latest finish to match the earliest finish. Then we set the latest start for activity H as the latest finish minus the duration, or 15 minus 2 equals 13. We work our way toward the start by going to activity F. Here the latest finish is the latest start of the following activity. We calculate the latest start by subtracting the duration from the latest finish. We follow the same process for activity G and move to activity C. The latest finish is the smaller of the latest starts of the two following activities. We calculate the latest start for activity C. We follow this process until we reach the start activity, and all of the latest start and finish dates are calculated. Note that the latest start and finish values in the network have been updated. This is the completed project plan. We now transition to a discussion on slack time. We recall that slack is the length of time an activity can be delayed without impacting the overall project. We see the formulas for slack. Slack equals the difference between the latest start and the earliest start, or the difference between the latest finish and the earliest finish. Remember that an activity without slack is on the critical path. The table displays the summary of the starts, finishes, and slack for each activity, along with whether the activity is on the critical path. Note that 5 of the 8 activities are on the critical path. Here we have summarized the project with the critical path highlighted in red, slack shown for non-critical items, and the project duration is identified. Key points to remember. Project scheduling starts with proper preparation. The project requirements are gathered, which then translate into the activities necessary to meet those requirements. The precedence of activities is defined along with the time, resources, and money required for each activity. We started with the Gantt chart, which lists the activities and shows the time duration for each. The order of activities is also shown. Next, we reviewed the critical path method, or CPM, and the program evaluation and review technique, or PERT. Both are network techniques that link activities by their relationships. Time, resources, and cost data are added to identify the critical path. The big difference is that the PERT technique uses a more complex model to estimate the time. Next, we reviewed an example using the Activity on Node network. Each node represents an activity with arrows connecting the nodes based on their precedence. Once the basic network is created, we calculate the earliest start and earliest finish during the forward pass as we move from the start of the network to the end. Then we calculate the latest start and latest finish during the backward pass as we move from the end of the network back to the start. At this point, the critical path is identified as the longest time path through the network. If the critical path is delayed, the entire project is delayed. Finally, we look at the slack time, which is the time that an activity may be delayed without affecting the overall project. Activities on the critical path have no slack.